let's move on to the main subject of the day. And that's going to be, flavors. We talked a little bit about that the other day, some of the flavors. And I'm going to start with waves. It's important to start with waves because we need to get the wave out of the wave. We wave it away. We wave the wave away, okay? Here it is. Let's start real quick with a history of the wave, okay? And here it is. They had the ether all the way to almost all throughout the 19th century. And in 1887, Michelson and Morley, they convinced mathematicians who call themselves physicists, right, that the ether didn't exist. Or a lot of them became convinced, right? And so what was it that was waving if not the ether? Because that's what they thought was what the wave was. Light, right, was a waving of the ether. And these guys apparently proved to many of them, to the many mathematicians, that there is no ether. So then what is it that was waving? And so rather than answer the question, what they did, they looked for other outlets, and one of them was that they started making calculations based on the speed of light and time. They use time and speed of light, and they say, what's happening is we have a shrinking of the distance, or distance traveled, or length, or whatever, right? Because for them, there's no difference. And so they started going in a different direction. Instead of saying, instead of accepting that they didn't know what was waving, they said, well, it's still what's waving is the ether, but we can explain the results, the null results of the Michelson-Morley experiments, right? And they did more than one. Okay, so what happened? By the turn of the century, you had these milestones here. You have Max Planck show that light comes in discrete bundles of energy, the famous quantum, right? That's when quantum really started, you could say. Maybe not the name, but surely, slowly but surely, the bundle of energy became part of mathematical physics. Okay, that's when it started. Einstein, he demonstrated the Planck quantum could be used to simulate the photoelectric effect. You had this bundle of energy that hit an electron and kicked it out of its atomic orbit, or whatever, because they didn't have an orbit, they didn't have a notion of that yet, but kicked an electron, and the electron started flowing, and that was electricity. So that's how they explained the photoelectric effect. He won the Nobel Prize in 1921 for explaining the photoelectric effect based on the quantum. Okay, so throughout the 20th century, especially the first quarter, right, what happened was that they had these two versions, the wave and the particle. Especially when Louis de Broglie, he came up with the idea that particles also have wave-like behavior, especially the electrons. So not only was it light, but also the electrons and maybe other particles that had wave-like properties. And because of that, they started saying, okay, we're going to have this duality. Particles, no matter whether they're photons, electrons, or eventually neutrons and protons, they'll have wave-like behavior as well. Okay, so it's not only a particle, it's a wave. We have the wave-particle duality. And we have this all the way to today. Nothing has changed. Everybody believes in wave-particle duality, and mathematicians like it because it allows them to cover all the bases. They can explain anything with that, because if you have a malleable hypothesis, a malleable assumption, right? Well, you can use it for this or you can use it for that. And when you want to explain something that relates to wave, you use the wave. And when you want to explain something with particles, you use the particles. Turns out that the bundle of energy is not a particle, because energy is not a particle. Energy is a concept. So what is a particle? Well, we discussed that last time. Particle is not a particle. It's not the famous, Newtonian corpuscle. It's not a little ball, a little bead. Quantum just means, quantum particle means number. That's all it is. It's a value. What they're accelerating are values. They're just going to talk about, what they're accelerating in terms of energy or mass or whatever, not in terms of balls. And so they don't have physical interpretations for all these things. That's the issue. Okay. And to this day, we have no physical interpretations from the entire mathematical establishment, where they simulate it with real balls. They simulate it with a ball. They'll put a point, they'll put a little ball, and then they say, oh, don't mind the ball. That's just because I need to put something on the screen. But if you want to really understand it, you got to come to mathematics, and we're going to show you, the numbers, the equations. Okay, that's what they're dealing with. Okay, but what's the problem with the wave? If there is no such thing as wave, why? Why is it an irrational proposal? Because that's what it is. It's an irrational proposal. And there you see it. Okay, wave is made out of what? Vectors. Actually, two fields. What's a field? You see it there at the bottom. It's a value at each point in space. So field means values, many values around something, and those we're talking about numbers followed by units, predefined units, standards that we created. And so we have these two fields, which are just a bunch of numbers with units, and each one of those fields is made out of vectors. What are vectors? Well, it's magnitude and direction. And actually, it doesn't even have direction. That's the issue. That's wrong too. And one of the things that you'll see with it is they put it in motion. And here, let me see it. I see if I can put it up there. And so they have this. They have these vectors, and they're moving. It's scary stuff. You have all these mathematical concepts, and they're moving. And that's how they portray them. And so what are we supposed to think about this? You're talking about a concept, a bunch of numbers that are moving. That's what you're staring at. Okay, so yeah, it's a problem. And, wave is not a thing. What it is an abstract concept made out of fields, which are concepts, and the fields are made out of vectors, which are concepts. And it turns out the vectors are weird because, vector of math is not the vector of physics. And we have to make a distinction there just in case because, in physics we use vectors, but it's qualitative only. Vector is depth, breadth, and elevation. Those are the three vectors of physics, okay, which is motion in three mutually perpendicular directions. That's what a vector is for the purposes of physics. It's qualitative only. And in math, they don't have vectors. They don't have dimensions, and they don't have coordinates. What they have in math is magnitude. And they're talking about no orthogonality or direction because these are qualitative concepts that don't belong in math. They're just talking about number lines that have only magnitude. And it's so weird because they put, a line with an arrow. And the arrow is not direction. Arrow shows that numbers are increasing. That's very different than physical direction, like, that direction. That's not what that arrow means. But that's what's so misleading about that arrow because people think it has to do with direction. In fact, they define a vector as magnitude and direction. No, a mathematical vector does not have direction. It only has magnitude. And it takes a while for people to catch on to that argument. Okay? So I'll let you roost on that. Okay, so what's the issue? Here you have Stephen Hawking. He confirms what I just said. Okay, Stephen Hawking, he was a so-called mathematician who called himself a physicist. Says, in relativity, there is no real distinction between the space and time coordinates, just as there is no real difference between any two space coordinates. Right, because they're talking about number lines. They're not talking about coordinates, vectors, or dimensions. So space-time is not four-dimensional. Space-time is four-number-lined. Only has number lines. And here you see an example. We had used to have this. The meter used to be a solid rod of platinum, and this was standard number 27, which became the meter for the United States for many years, all the way to 1960. If you wanted to know what a meter looked like or what it measured, well, you had to measure against that one, which was the standard for so many years, 100 years, right? And that was replaced in 1960, and you say, well, what was it replaced with? And this is where you got to get a beer or something. They replaced it with motion. Yeah, just like I'm saying. They replaced it with motion. So you had this stick, right? Metal stick, right? And they replaced that with the unrolling of the measuring tape. What was it that they replaced it with? Well, they replaced it with this. They replaced it with the meter, the length of the path traveled by light in a vacuum during a time interval of so many seconds, right? Which is the inverse of the speed of light. Okay, so why? Because length is a measure of distance in the religion of math. Okay, they don't see a difference between length, distance, or distance traveled. For them, it's all the same because they're going to have to unroll the measuring tape, irrespective of which of these qualitative, words, right? Especially length and distance, irrespective of what they really mean. Length belongs to physics and distance belongs to physics. Neither one of those two words belong to math. The only one that belongs to math is the distance traveled, which is the unrolling of the tip of a measuring tape, or counting tiles, if you will. You measure a tile, say 1 meter, that's going to be your standard. You use 10 tiles, that's 10 meters. So you counted tiles. It's you laid tiles or you unrolled the measuring tape. That's what it is. But the funny part is, it says light in a vacuum. Turns out in the religion of math, math phys, right? There is no such thing as vacuum. You look up and it says space devoid of matter. All right, that's the definition of vacuum, but it's not, because vacuum, any space in which the pressure is considerably lower than atmospheric pressure. In other words, vacuum always has something in it. That's what they say. That's what people are told to repeat like a parrot, right? And in QED and QCD, right, you have this vacuum. It says vacuum fluctuations that produce transient virtual particles. So whenever you don't have real particle, you have all these virtual particles popping from the void. So there is no such thing as vacuum in mathematical physics, okay? And they have these vacuum fluctuations. What is it? The temporary random change in the amount of energy in a point of space, okay? And so they follow good old Aristotle there, who said, nature abhors a vacuum. Yeah, there is no such thing as vacuum in the religion of math, and they never established the difference between length, distance, and distance traveled. So here we educate them and show them what the difference is, just for people to know. Distance, this is according to them, right, the mathematicians, is a numerical measurement of how apart objects or points are. Absolutely not. Okay, distance is separation. That's what it is. It's a qualitative concept, okay? And then they say in physics, actually mathematics, right? Distance may refer to what? A physical length. No, not at all. Not in science, not in physics. In physics, what you see at the bottom. Distance is what lies between lengths. Length is what an object has. Distance is what an object does not have. Distance is the separation between 2 points. It could be within the length, but now you're unrolling the measuring tape if you're going to do distance traveled. Otherwise, this is just separation, okay, between objects. Okay, so distance lies between lengths. Once you learn that, you get it. You're all set, right? What mathematicians use is distance traveled. They don't use distance. They don't use length at all. They just unroll the measuring tape. They look at meters, feet, inches, whatever. Those are unrolling the measuring tape. They're interested in numbers. They're not interested in qualitative notions at all. And that's part of the problem. Okay, but what's the issue with a wave? The issue is that we have this wave, and we have to determine, is there a physical object called a wave? And they say, well, the wave, extends infinitely, or it travels. And what are you talking? What do you mean the wave extends or wave travels? And here you see what they have to answer. This is what they have to answer. Okay, here it is. Watch it. There you see it. Either it extends from the Andromeda Galaxy all the way to Earth uninterruptedly, or it travels as a little sailboat from there to here. Which is it? Does it travel or does it extend? That's what they have to answer. Where does a wave begin? Where does the wave end? And again, what is it made out of? Is it made out of vectors? And so all these questions are stuff that they have to answer, and they never do. They never tell you whether it extends or travels. Okay, and this is the only question that, a mathematician needs to answer. Who proposes the wave? And the problem with a wave, again, is that you will not find it anywhere in quantum mechanics in the standard model. Right? You would think that if particles have, duality, right? They are both waves and particles. Well, where's the wave chart? I've always seen the standard model, which is particle, a bunch of balls, okay? And it looks more or less like this. Okay, do you see any wave there? It looks like all particles, right? And so where does the wave come in here? Why don't they put a chart like this for waves? And again, it wouldn't make any sense in great measure because a wave is just a bunch of vectors. It's just numbers. And so they use that concept, but they turn it into a physical object. They say, oh, the wave moves or travels or whatever. Okay, so they replaced the particle with the waves with particles. That's essentially what's happened. That's why quantum has survived all these years. And they give lip service to the waves. That's what's happening. Quantum uses wave only to justify why discrete particle is everywhere. So if they want to show that the particle is everywhere, they bring in the field concept, which, you have two fields make up a wave, electromagnetic wave. And so now you can fill the whole space. The wave is everywhere. And, what kind of explanation is that? That's like God being everywhere. God is everything. Yeah, that's a great explanation. I learned a lot with that. And the wave is everything as well. It's everywhere. And so you haven't explained anything. You either use the particle or you use the wave. And so they have this particle collapse, the wave function collapse, and they give a lot of interpretations to that as well. But essentially they're saying, the reason you can measure a particle is that the moment you touch it with your probe or whatever, that's when the wave collapses. So we have the wave that extends throughout the universe, and suddenly it collapses to a point right there where you put the stick. Yeah, tell me about it. Okay, and otherwise quantum mechanics always uses the particle, and that's all you'll see in the standard model. Okay, so this is the problem. The problem is they don't have any physical interpretations for any of this, because again, what they're using is the notion of the particle to explain almost everything, and they're going to be explaining all these things in quantum with particles. They only bring the wave when they have to explain, why the particle is everywhere or at two places at once or whatever.